Ladies and gentlemen, my name is He Liu and I come from China University of Petroleum, East China. Today it's my honor to give a speech on behalf of my supervisor, Professor Zongxian Wang, and the topic of my presentation is transformation of vanadium porphyrins in heavy residue during non-catalytic thermal upgrading process on hydrogen. This is the outline of my presentation, including the following 6 parts. Firstly, I will give a brief introduction of our work. As we all know, the production of heavy oil gradually increases in recent years, and the heavy oil contains a majority of heavy metals. Among these heavy metals, nickel and vanadium are the most abundant and troublesome. They could cause the deactivation of catalysts in catalytic process. Even in the non-catalytic thermal process, they would also promote the dehydrogenation reactions and lead to a faster coke formation. All these effects would deteriorate the product's distribution as well as the quality of products. Therefore, it is important to study their transformation during the upgrading process. It can reveal the essential behavior of inherent metals, and it can also benefit the catalyst design during hydroprocessing. Then, I want to review the recent researches about the transformation. The metals in heavy oil are generally considered to be present as metal porphyrins and metal non-porphyrins. The structures of metal non-porphyrins remain a lot of controversies, so researchers mainly focus on the metal porphyrins. Since the heavy oil is a complex system, the early studies commonly utilize the simple model compounds to study their transformation, including the mechanisms and kinetics, the morphology, and the hazards of the final metal deposits. Based on these studies by using the simple model compounds, researchers have also tried to study their transformation by using the real oil system or oil subfractions, and many characterization methods have been tried, including the XAFS, the UV visible spectroscopy, the EPR, and the FT-RCMS. And in these previous works, the great progress have been made. However, challenges still exist. It can be mainly attributed to the low concentration of metals, the higher reactivity of metal compounds during the hydroprocessing, as well as the limited characterization methods for the petroporphyrins. In order to resolve these problems, we have made our attempts in this work. To increase the concentration, we have selected the heavy residue from Canadian oil-side bitumen with high content of vanadium, close to 200 ppm. And then we isolated and purified the petroporphyrins from the feed. In order to decrease the reactivity, we have selected the non-catalytic thermal upgrading process on hydrogen. As for the characterization method, since the FT-RCMS have been greatly developed and successfully used to characterize the complicated hydrocarbon system, so we have chosen it as the characterization method in our work. In the experimental section, I will go through the sample preparation, the thermal experiment, and the final analysis. This is a separation scheme for the petroporphyrins, including the solvent extraction with the acetylnitrile, and followed by the silicate gel column chromatography. After the separation, we have obtained 6 subfractions from the feed and labeled as F1 to F6 respectively. And then we measured the metal contents in these subfractions. From the red digital, we can see that the nickel contents in F2 and F3 are particularly high, and the vanadium content in F2 is low. So we can see that the nickel tends to concentrate to F2. And from the blue digital, we can see that the vanadium contents in F4 and F5 are particularly high, and their nickel contents are low. So we can see that vanadium tends to concentrate to F4 and F5. In order to detect the metal porphyrin, we have obtained the UV visible spectrum. From this figure, we can see that the F2, which is the red plot, presents characteristic absorptions of nickel porphyrins, and F3 shows no obvious absorptions of petroporphyrins. And the last three subfractions show characteristic absorptions of vanadium porphyrins. Since the vanadium contents in F4 and F5 are particularly high, and meanwhile the absorptions in F6 are relatively weaker, so we have chosen the F4 and F5 as the targeted vanadium porphyrin enriched subfractions in our work. Using this subfraction, we have carried out the thermal experiment. After the thermal experiment, we obtained the final products. The feed and the products were then subjected to the FT-RCL mass analysis, as well as the UV visible spectroscopy. And the typical conditions for the mass analysis is listed briefly and merely referenced from literatures. Now it's the resultant discussion. Firstly, I want to show you the result of the UV visible spectroscopy analysis. From the figure, we can see that the characteristic absorptions of vanadium porphyrins at about 570 nanometers gradually decreases with time increasing, and in the products for longer reaction time, there is also a new weak absorptions at about 630 nanometers, which can be assigned to the hydrogenated intermediates for petroporphyrins. So from this phenomenon, we can see that the petroporphyrins have been hydrogenated during the upgrading process. It should be noted that the decrease of the absorptions cannot all account for the hydrogenation reactions. This is because their absorptions are not only related to their amounts, but also to the properties of oil matrix. Then we measure the feed and the products by the FT-RCL mass. From the figure, we can obviously see that the center of the mass spectrum gradually shifts to the lower molecular mass range. And in the feed, we have merely identified 3 main species of vanadium porphyrins, including the typical vanadium porphyrins labeled as N4VO, and the sulfur and oxygen-containing vanadium porphyrins labeled as N4VOS and N4VO2, respectively. All these species have been identified with different dBe values. Firstly, we analyzed the transformation of N4VO porphyrins. This is the variation of dBe distribution. From the black column, we can see that in the feed, the most abundant types for N4VO porphyrins are ETIO and DPEP. And after thermal treatment, we can see that the dominant dBe value have shifted from 18 to 17. And in the products for longer reaction times, we can see that the species with dBe of 16 are also observed. Consistent with the UV visible analysis, we can see that the N4VO porphyrins have been subjected to the hydrogenation reactions. Here, we also present the variation plot of their relative abundance versus time. From the plot, we can see that the abundance of species which dBe is 17 increases initially and then decreases, in contrast with the species which dBe is 18. According to previous researchers and this phenomenon, we can infer that in addition to after the hydrogenation reactions, the petroporphyrins may have been subjected to the rapid hydrogenolysis reactions. Then we analyzed the transformation of sulfur-containing porphyrins. Similarly, from the black column, we can see that the dBe values for the most abundant types in the feed are 23 and 24. And after thermal treatment, the dominant dBe value have shifted from 24 to 23. Here we also present the variation plot. It is interesting that the N4VOS porphyrins with dBe higher than 21 present a very similar variation with the typical vanadium porphyrins. This may be because that the sulfur-containing porphyrins with dBe higher than 21 may occur from the N4VO porphyrins by the addition of benzosulfone. In addition, we can see that the sulfur-containing porphyrin with dBe of 20 and 21 may present a very different variation from other types. After thermal treatment of 13 minutes, we can see that they almost disappear in the products. This may this indicates that these two types species may be more easily degraded by the upgrading process and present a different structure from other types of sulfur-containing porphyrin. And with time increasing, they appeared again in the products. This can be assigned to the hydrogenated intermediates for other types of sulfur-containing porphyrin. According to our previous work, we have proposed the most possible structures of sulfur-containing porphyrin with DBE of 21. By the molecular simulation, we inferred that the most possible structures may be the cyclic, the fibrin cyclic cell ether attached with the porphyrin. And this structure is more reactive than the benzosulfane, resulting in the faster degradation during the upgrading process. Next, we draw the corresponding iso-abundant plots of DBE as a function of the carbon number. And the plots in the higher DBE part have been enlarged on the right. From this figure, we can see that the carbon number in the center of the mass for each type of the vanadium porphyrin became smaller with time increasing. This is the same case for the sulfur-containing porphyrin. This phenomenon indicates that the N4VO and the N4VOS porphyrins have been subjected to extensive thermal cracking reactions during the thermal upgrading process. And finally, we analyzed the transformation of oxygen and nitrogen-containing porphyrin. And this is the corresponding iso-abundant plots. We can see that after thermal treatment for 30 minutes, a considerable proportion of new types of oxygen and nitrogen-containing porphyrin have been identified by the FDR-CMS. And with time increasing, the emerging vanadium porphyrin have gradually disappear, and with the reaction time is 2 hours. Only the most abundant types in the feed of the N4VO2 porphyrins can be survived from the upgrading process. Here we also present the expanded mass spectral at a mass-to-charge ratio of 542 and 543. From the accurate mass measurement and the corresponding isotope distribution, we can clearly see that the new species of oxygen and nitrogen-containing porphyrins have been formed after thermal treatment of 30 minutes. As for the possible reason, these new species can be converted by the chemical transformation. On the other hand, as we know that the metal porphyrin can be trapped by the large polar molecules such as asphaltenes, and the vanadium porphyrin enriched subfractions present a higher polarity. So after thermal treatment, the metal porphyrin may be disassociated from the large polar molecules. In summary, from the analysis of their transformation of different vanadium porphyrin species, we can see that they have been subjected to the hydrogenation as well as extensive thermal cracking reactions. And the sulfur-containing porphyrin show very similar structural transformation with the N4VO porphyrins. A considerable proportion of new types of oxygen and nitrogen-containing porphyrin have been identified after thermal treatment for 30 minutes. They can be converted by chemical transformation as well as dissociation from the large polar molecules. On the other hand, the analysis of their transformation may benefit the catalytic design during the hydroprocessing. Firstly, the catalyst should have active hydrogenolysis property since the petroporphins have been subjected to thermal cracking reactions. And since the different vanadium porphyrin species have been present different carbon number distribution as well as the different reactivity. So the catalyst with micropore size distribution will be active for all the species to be removed. As for the future work, I think we will continue to study the effect of thermal conditions for on transformation of these petroprophins. In our previous work, we have successfully identified the nickel porphyrin by the FTRCMS, so we will examine the transformation of nickel porphyrins during the process. And at last, we have inferred that metal porphyrin may be interacted with the asphaltens, so it will be meaningful to study their transformation of petroporphins in asphaltens and mild thermal pretreatment. And last, we would like to thank the State Care Laboratory of Heavy Oil Processing in China University of Petroleum and Professor Chen Shi at China University of Petroleum Beijing for the support of funding and equipment using. This is our research group, the research group of heavy oil chemistry and thermal processing. And welcome to visit our website. And that's all my presentation. Thank you very much for your listening.